And for today's class, it's going to be a lot more toned down versus what we got through. Sections 2.7, sections 2.8, they're going to be on the exam number 1. That's really going to emphasize section 2.7 more than anything. You'll have to calculate the derivative by using the definition of the derivative. That's going to be the main takeaway on what goes on in exam 1 for those sections. But what we're doing today is we're going to now take a look at what happens if we just add some theorems on calculating the derivatives. What are the actual differentiation formulas? And they are quite nice. So getting through chapter 2 is tough, but once you get into chapter 3, not as bad. So our next exam will happen when we return on Monday's class. It's going to cover just these sections like we mentioned, and the sample exam 1 problems are posted right here. If you have any questions on those as you study, then I'll be very happy to help. And even if you have questions over the weekend, I will be available over the weekend as well. Well, any questions at the moment, folks, about the exam or other matters?
Monday?
It's going to be next Monday, yes. Okay, well, let's get started then, folks. We're in section 3.1, where now we're going to take the information that we've been working on, building the actual derivative from scratch by the definition. And then after a lot of work is done, if you're interested in where these formulas came from, it's from a class called elementary analysis. If you're going to major in math or a minor in it, then we'll probably get into this material. And that's where all this stuff is proved rigorously from scratch. How they did it is they went to this section. They take this formula right here. Then you go to this section. There they are. Take your definition of the derivative, this right here, combine it with the limit laws, and suddenly you have a ton of really, really powerful tools for calculating the derivatives. So essentially, that's where all this came from. Those original limit laws that we saw way in the origin, in the beginning of the course. If you're curious where the limit laws come from, elementary analysis shows how to actually rigorously prove each one of those as well. So it's kind of a cornerstone course if you're going to do just lots and lots of calculus likely. But let's take a look at these, see how they go. First thing that looks weird is this d by dx. That's just our differentiation operator. And it's saying differentiate x to the power of n, and that's your result. I want to write this formula out one more time. If you were to write this in Newton's prime notation, it would look like this. X to the power of n prime is saying differentiate it. Let's take a look at what the formula says right here. The exponent comes down and becomes a coefficient multiplying. So there it is, n. And the new power on x is 1 less, no matter what that exponent was, whether it was negative, whether it was a root 2 exponent, it'll be an n minus 1. So that's our first amazing powerfully formula to work through. If you were doing the definition of the derivative and you had, say, this function, y equals x to the power 5, then that is a really long problem to get through. But this formula says here, if you want to calculate the derivative, it would look like this. Either call it y prime, or you could call it dy dx. It'll be equal to, first thing that happens through the formula is we look at the exponent here. Just drop it down. It's now a coefficient, so 5 comes in. And anyone see what the new power of x should be by the formula? Exactly, power 4. And we're done. We did it, folks. We differentiate something. Again, this is a problem no one would ever want to do if we had to do it from scratch. So this is a massively powerful rule. And we have another set of nice rules right down below. Kind of the way I'm going to go through these notes is we'll look at each one of these rules, see what the essence of it is, take a look at an example, and then down below here, we'll do some practice problems. I would love to get through this question here, forming a tangent line equation. And this is the bonus question. It's something we're going to look at a lot in chapter 4, interpreting what happens when we differentiate and evaluate the derivative. This is a challenging problem because differentiation is already new. And once you've differentiated, get a number, if we can't say what that number is good for in something with context like this, it's almost as if the derivative is useless. So in a certain sense, we don't get through this one today, it's okay, because we will see quite a lot of these as we practice. Let's go back to the top and try out some more problems. Well, let's say we didn't have y equals x power 5. Maybe you had y equals, let's make it 2x to the power of 1/3. And we want to differentiate that thing. Now, the 1/3 here is actually totally fine. N could be any real number. It could be 1.3. It can be pi. Any exponent is valid for here. Even 0 is valid as an exponent. But the thing is new is that 2 is a constant that's multiplying. So we use the constant multiple rule. Here's the main essence of that rule. If you're differentiating and there's a constant multiplying your function, there's our constant. F of x would be x to the power 1/3. Then that's okay. Your constant just comes right out here. And you just differentiate the original function. So that's the idea of the constant multiple rule. It's supremely nice to have because it's always going to make your work a little bit easier. This kind of function here, you can use the power rule on it, but you can't use the power rule on this until you combine it with that multiple rule right here. So here's how this one would differentiate. You can call it dy dx like we did above, or you can just call it y prime. So upon differentiating y prime, the constant multiple rule says, the moment you see a constant, you can just copy it down. Here it is. That 2 copies in. Now this part where it says d by dx of f of x, that's where we return to this right here and differentiate. But that's a power function, so we use the power rule, and it's this little game again. Exponent of 1/3 will come down and multiply as a coefficient. And it doesn't matter if there's a 2 in front of it, it'll just go in like this, times 1/3. Then the new power of x is 1 less. So we're subtracting 1, just visualize subtracting 3/3. You'll get a new power of negative 2/3. So that's finally our first derivative. Any questions with that so far, folks? Okay, if we say simplify it a little bit more, we could write this as 2/3 x to the power of negative 2/3. And you really have a lot of options now at this stage. Even though that's a negative exponent, I'm personally not worried about that. You can leave your negative exponents right where they sit. If it bothers you, it's negative, but you want to force it positive, you could write your answer this way: 2/3 x to the positive 2/3. But that's a stylistic choice of writing your answer, in my opinion. In this class, as far as grading goes, I'm fine with this answer or this answer. Let's emphasize both are acceptable. Both full credit. Seems faster to write than saying acceptable for some reason. Well, any questions, folks, with this rule here? Okay, so really the biggest rule, I'd say, the biggest takeaway in these notes is really this one. The power rule is going to be used kind of over and over again on a lot of different problems. And it's going to become kind of tricky to see when do we get something that's a different rule and the power rule doesn't even work on it. We'll see a couple of examples there. But now here's our next scenario. We can differentiate a power function like x power 5. We can differentiate a multiple of a power function. But what about this function? Y equals 3x squared minus 7x plus 5. We actually calculate the derivatives of these kinds of things from scratch, finding slopes of tangent lines and so on. It's a really long process. But this is what this rule is saying. If you have two functions, either being added or subtracted, plus and minus there is just saying one option or the other, then all you do is differentiate the first function plus or minus the derivative of the second function. So in other words, derivatives of a sum of functions is just the sum of the derivatives of those functions. They state the rule for two functions, two different terms, but it automatically applies for as many terms as you want, as long as you have finitely many. So we can use the sum rule even with three different terms altogether. So let's give it a try. I'll call this one dy dx. When we go to differentiate, this is what the sum rule is giving us altogether. we just go term by term. Differentiate that one first. That's two other rules though, because there's a constant 3 multiplying the power function. But our second rule said, don't worry about the constant, just copy it in. There it goes. Differentiate x squared. Anyone see what the derivative should be of x power 2? Exactly, this would go to a 2x. Oh, let me fix my work here. There we go, 2x. Have to multiply. If you put a power 1 here, I think that's excellent because that's the direct use of the power rule. But it's typical we would simplify that on the next step. So it becomes kind of optional. I think after a while, a lot of people just start writing it power 1 like that. For the moment, just because we're still using that rule, let's leave it as power 1 to emphasize we took 2 minus 1 from that power rule formula. Well, that finishes off that term. Now let's focus on term number 2. We want the derivative of that. And in a certain sense, it's kind of tricky because if you're using the power rule, we'd like to know what the exponent is. What would you say the exponent is of just x? Right, it's just a 1. So if we throw it in, it's only for emphasis. I'll put it in here lightly. I'm going to delete it hereafter since typically, again, it's not written in when you see problems. But now if you differentiate this, nothing much happens, right? The 1 comes down, multiplies -7. So we'll have -7. The new power on x is 0. Now, that's a little bit weird. If all you write is -7 right here, that's the better answer. I'm forcing myself to take an extra step if I write x power 0. But keep in mind, I think we mentioned this before, x power 0 is 1. So that's not too bad to put the 1 in there just to help out, but it's going to be just a -7 on our next steps. Does that make sense so far, folks, on the first 2 terms we have? Okay, so we have this done. All that happened is 2 came down, multiplied, and we're going to get a 6x. This one's done because x is to the power 1. You're just going to get a -7 and nothing else after that. But what about this one? And we know what the derivative of that should be. 0, good call. There's another rule that explains why, but if you wanted to, you could think in these terms. I think we did this once as well. You can insert x power 0 because it's a 1 multiplying. If you differentiate, 0 comes down, wipes out your 5, and x is now to a power of 1 less, -1. Sounds bad though, but there's still a 0 multiplying it. It's just gone. So the punchline to this, which is a bona fide rule on its own, is that turns to 0. I'll write +0 right here on the notes just to show, yes, we did it. It's right here. But typically, you wouldn't even write that 0 once you differentiate the constant 5. In fact, no, it's not. Darn. There should be a rule there. There isn't. But that's a rule in its own right, that if you differentiate a constant, you get a 0. You know what? Let's make up our own rule. I think the author did put this in, or maybe I neglected it. Oh, geez, I was going to put in a border. Let me try again. There we go. Well, let's call this the derivative of a constant. All we have to say is, let C be any constant. It could be 0, it could be 5, it could be the square root of 2, or maybe E for Euler's number. Then the derivative with respect to x of that constant C is just automatically 0. So anytime you see a constant, you could use the trick of putting in x power 0, visualize 0 coming down, multiplying, but this is the better way to think of it. Your constants just die. In fact, we've done that once. That was one of our second to last problems in section 2.8. We did take the derivative of a constant and we used the definition of the derivative, and we got 0 out right away. So that's where we're at. They're all 3 are done. So we don't need check marks if they're all done. And so this derivative just becomes 6x minus 7 when it's all said and done. Any questions at all, folks, on getting through that one? Okay, I'm going to put this in red, not because it's wrong, but it wasn't in the original notes, so that was a addition edit that we threw in the middle. Now let's do an example on this one. To me, this example is very, very tricky. It's extremely confusing. What if you said f of x was e to the power of 5? Let's differentiate that, and you see what the derivative of e power 5 ought to be. Turns out it wouldn't be 4e, but I know what you mean. It's tempting to use one of these kind of rules on it. Say, for example, if it was a different function, g of x equals x to the power 5, that one we can use the power rule on it, and we can say the derivative of g at x is 5 will come down. The new power on x would be 4, and that's by the power rule. But what made all that work is x is variable, it's not constant. Over here, e itself turns out to be constant. Let's take a look at it. If you plotted y equals e to the power 5, it's not plotting for me. How can I make that plot? Let me try again. F of x equals e power 5. There we go. It's up there somewhere. There it is. That's our constant function. The derivative is going to give you the slope of this line. It has to be 0, exactly. But that's the trick. That was constant and it didn't look like a constant. We're used to things being more like, say, the 5 there, or an 11 or a 7/2. But sometimes constants are disguised like this. The derivative is 0 nonetheless. Let me show you an even worse one. Let's say y was cosine of, how about 3.9? If it was cosine of x, in a section in this chapter, they'll tell us the derivative is a sine function, negative sine of x. But if x is missing, that's just another constant, and the derivative, y prime, would be 0 on that one. So that's the derivative of a constant, and it's a nasty rule because if you're going to use this rule, which we'll have to, you have to be very keen on what do we mean by constant. Stuff like this, where it's missing the variable. This one is not constant. Any questions, folks, so far? Exactly. It'll be 0 in the derivative each time if your variable is missing. Other questions so far? Okay, well, I have 2 more rules, and then we'll get to just practicing general kinds of problems with all these mixed together. These are the really kind of fancy rules. They're almost the best case derivative you would ever want for this one right here. Derivative of the natural exponent. When our author says natural exponent, they're referring to the number e. So natural exponent is e, which is approximately 2.71. Now this function, e to the x, is like the world's best exponential function as far as calculus is concerned. And look at what this is saying. If you differentiate the base e exponential function, e to the x, the result is exactly itself. That is a unique function. There is no other function that does this. And so, I mean, there's not much to practice with. If you have y equals maybe 7 e to the x, and you go to differentiate, y prime would be, here's the constant multiple rule, 7 copies in, differentiate e to the x, you get e to the x. This is super tricky though, but question first, sorry. Exactly, that's what forces it to be constant right here. It's missing x. Yeah, this one right here with cosine 3.9 as well. Other questions so far? Yeah, go ahead. In this case, yeah, really bizarre, right? It's like we did nothing at all on it. Other questions so far? A capital F, say where? Oh, that would just be same kind of stuff. They're just using different style to indicate the function. Yeah. Well, one thing I want to point out with on this is that's a nice derivative, right? The formula doesn't get any better than it, but actually it's not so nice. The thing you have to worry about and be very careful is where is x? If x is right here, you're using the constant multiple rule. Exponent comes down, the exponent's reduced by 1. But if x is right there, that is not a power function. X will not come down. There won't be x minus 1 here. You just get the original thing back. That's extremely subtle. So always look at the difference of where x is. As a base, you do one thing, but as an exponent, it's now totally different, which is definitely kind of wild with these. Well, that's the natural exponential function, base c exponential. But if it's a generic exponential function, like say a to the x, the formula does modify, but just by a tad. You have to multiply by the natural log of that base. Well, actually with this formula, the same sort of thing is happening. Because if we say y equals, let me try again, e to the x. This is the formula to use for sure. The derivative is just e to the x. But what if you use this one? We would have said y prime or dy dx is e to the x multiplied by the natural log of the base, which is e. Suddenly that feels different, right? But there is a trick here. Anyone happen to know what log base e is, the natural log base e?
1.
It's exactly 1. Good call. So that's a cancellation immediately. And you just get y prime equals e to the x. So the idea is that's a specialized formula. And this is the general one that works for every single exponential. Yeah, go ahead.
We could write it down.
Sorry, say again.
We could write that down.
This right here?
Yeah.
No, I would say the best way to do it is like what we did over here. Yeah, this was more just showing what the formula is trying to say.
Sometimes the most important thing.
It does, and that's one of the reasons this gets to be called the natural exponential function. It causes something natural to happen, not just with derivatives, but with other things as well. But other questions so far? Okay, let's try this one out with a more bona fide example. If y was equal to 2 to the power of x, that's a perfectly fine exponential function, just like e to the power of x. Even the bases are somewhat similar. Base c is about 2.71. Now, if you were to differentiate this thing, it would be dy dx or y prime. And here's how this one goes. First, it's just 2 to the x. But then you multiply by the natural logarithm of the base. The base is still 2, so 2 would go inside there. So that's how we would really use this kind of formula right down here. Well, any questions, folks, on that last one? Okay, so that's our run through, and that's it. That's all the new formulas on this section. So now our goal is to kind of practice them, see how they combine together. And that's what we'll be doing on example 1. First, any questions or comments at all on any of these formulas? Okay, so let's try off. I'll put in black the original question. Let's call this part A. All it says is evaluate the derivatives. And let's start off with this thing. F of x equals negative 2x cubed plus 4x squared plus e to the x minus 9. So that's our function we'd like to differentiate. When you go to solve these on your paper, even though it's not something that's required for credit, it is a really, really good idea to start by doing something like this. Indicate the derivative some way. Either use f prime of x. Another option would be df dx if you like, just putting it there as an optional. I'll go back to the f prime. But the reason this is so important is we're going to see a lot of problems where you have to keep track of the original function, the derivative of that function, the second derivative of that function. And if we're not labeling what's what, it gets really, really fast to get a very tangled, mixed up mess. So the more you label what you're about to calculate, it's going to help quite a lot, especially in chapter 4. But now we're just going to go through the process going left to right. We're just going to separate this into the 4 different derivatives. First thing we use is constant multiple rule. And anyone see what this first portion will turn into?
Yes.
Negative 2 times 3x to the power of 2. Yep, that's pretty much what will happen there. So the process, if you like arrows, it looks like this. You first identify the exponent, put it down there. There it went. Multiply, then reduce your exponent by 1. So that's going to be the process each and every time we have a power function like that, a variable raised to a power. Yeah, go ahead. What do you mean by cross out the constant? Like, oh, right here? Yeah, absolutely. I think that'd be a fine strategy. So if you know that's just going away, you can just X it out. Actually, let's solve it that way, just as a reminder. I think it's the best way to do it. Other questions so far? Okay. And the more you do these kinds of things, the more it's going to just feel kind of like an automatic process. So if you wrote negative 6x squared and that's all you wrote, that's great as well. I would just assume you have done this enough. You're not too worried about writing down this intermediate step. I'll write these steps a lot in the notes as we're starting out because, I mean, we're just starting it out. If you go back to these notes, it's good to know how we got our answer. So let's go off to the next one. Same process, right? 2 comes down and it multiplies. The 4. New power of x is 1. So I'll just leave it as an x. That's what it simplifies to. What about the derivative of this one? What should we write down for e to the x? Exactly, it's itself. A very, very weird derivative. We'll go plus e to the x. We still have to simplify our answers. So here's my last step. You have negative 6x squared plus 8x plus e to the x. And that's pretty much all there is to it. If you have a function that looks like this, differentiate going term by term. Well, any questions, folks, on running through this one? Like, say, the exponent or the coefficient? We definitely are. I have a couple here that I'm going to get to. Let's jump to that one just to see how that goes. So on our part B, let's make it be a y equals. It could be an f of x equals a g of x, an uppercase f of x like you mentioned, or sometimes just a y equals to indicate the function. And I have 3x squared minus 6x plus 7, all of which is divided by the square root of x. So weird kind of function, but notice the danger about this right away. We don't have any rule as of yet that tells us how to differentiate a quotient of functions. I can't just differentiate the numerator and denominator and put them together. Turns out it won't work like that for this function. What we need to do is simplify until we get something that looks like this. We need to produce a bunch of terms separated by pluses and minuses, at worst multiplied by constants. We can't deal with this. And even if it looked like, say, root x times 3x squared minus 6x plus 7, we can't do that one directly either. We would have to distribute root x inside that entire group and begin simplifying. We'll do a problem just like that one as well, coming up as well. So the first thing we have to do with this is not differentiate, simplify first. Any questions first before we begin? Okay, as we go to do this, we're going to be using loads and loads of different exponent laws on some of these problems. And just as a reminder, if you feel a little rusty on exponents, there is review material here and a worksheet as well if you'd like. So let's give this a try. First thing I would want to do is let's go and write y equals. I'm going to take 3x squared divided by root x minus 6x divided by root x plus 7 divided by root x. So that was my first step. You can just divide this single term into all the terms into the numerator. Now I still need to simplify these. I can't differentiate in this stage until the base x appears in just one location. But here's our big trick on this. If you see the root of x, that's just x to a power. Anyone happen to know what the power must be? Exactly, we get a 1/2 out of that. If you say you have a generic nth root, n could be 2, it's still 1/2 a square root. It could be 7 or 3 for a cube root. This turns into x to the power of 1/n. So those are the major rules we'll use on this one. And so on the next step, we'll call this 3x squared divided by x to the power 1/2 minus 6x divided by x to the power of 1/2 plus 7 divided by x to the power 1/2. Next rule we have to use is if we have x squared divided by 1/2, the exponents are going to subtract. So we'll take 2 minus 1/2 on this one. So 2 minus 1/2, that's going to be 4/2 minus 1/2. And the new exponent is 3/2 on that thing. Over here, that's an exponent of 1. Think of it as a 2/2. Subtract 1/2 on that, and you'll get x to the power of 1/2 again. And new trick on this one, this is still a big problem for us. It's kind of surprising. The power rule is very, very specific. The base x is in a numerator, not in a denominator, if we're going to use the rule in this format. And so even this term is a problem. But here's our trick. We can go plus 7, x to the power of -1/2 to get the right value. So that's a bunch of exponent laws. Any questions, folks, on the exponent laws that got us to here? Okay, just a quick rundown. All I've done is subtracted 1/2 from this 2, 1/2 from this 1. And if you need to bring x above, all you do is you switch the sign of the exponent. And that's what achieves that. Finally, we're ready for the derivative. We'll call it dy dx. And this is the problem that I mentioned we really want to have. It's just a bunch of things separated by pluses and minuses, just like in part A. That's what we'll go down the line. First thing that happens here is 3/2 comes down, multiplying the 3. So it's 3 by 3/2. And we'll see what the new power of x should be. Exactly, we're going to subtract 1, meaning subtract 2/2. So we get power 1/2 altogether. Now we move over and just keep on doing these. 1/2 is going to multiply the -6 there, so you can simplify that now if you like, but I'll take this extra step. Copy -6 because it's a constant multiplying. This 1/2 comes down and multiplies it. And the new power, just subtract 2/2 from 1/2, we get -1/2. Now, down the line, this one's a negative exponent, but it doesn't matter. It just has to be a real number, any real number. -1/2 will come down and multiply the 7. Oh, what did I do there? I think I combined too many thoughts and forgot what the sign was. Let me just try one more time. Constant multiple rules, rule means you put plus 7 in first. Then the -1/2 comes down and multiplies it. And now new power on x, we take -1/2. We're always subtracting 1. So we're subtracting 2/2 to get -3/2 altogether. Well, I think we got it, folks. That's going to be our answer. All that's left to do to it is simplify as much as we can. Does it make sense, though, on how we got to this answer here? Okay, glad to hear it. Honestly, with some of these problems, the tougher work is what's in green, algebraically manipulating the function until it's in a form we prefer, where we can use the power rule, constant multiple rule repeatedly on it until we get our derivative. If you get stuck on any of the algebra, don't hesitate to write. I'll be happy to help. But we still have to simplify this stuff. It's nothing major. We just are going to call the coefficient here 9/2. X power 1/2. I'm completely fine with the fractional exponent. These are all really stylistic choices at this stage. Either call it root x, which it is, or x power 1/2. I'll call it root x. It looks fancy, but it's not required. Here we'll simplify and just get -3. This, we can just leave it exactly as an exponent if you like, x power negative 1/2. Or you could drop it to the denominator and call it a square root of x if you prefer. Again, for me, that's all stylistic choices. And you shouldn't have to take a lot of extra steps in blue to simplify your derivative. It should be pretty quick. So last one, I'll just write this as negative 7/2. X to the power, negative 3/2. And finally, that's our answer on this one here. This would be a very nasty problem if we had to use the definition of the derivative. It's achievable, but it would probably be pages of scratch work to get through all of that algebra. And that's the value of a good theorem. It just allows you to calculate really, really rapidly. Well, any questions, folks, on getting through this part B here? Okay, well, this is what happens when our exponents become fractional and the function itself is a fraction. So let's do something kind of related to the ideas here and take a look at this one. It is a g of x. I don't know why g, but it's a valid name for a function, so we'll go with it. It's equal to, I wrote down negative 5x multiplying x plus 1 to the power of 2. Well, it's a totally fine function, but when it comes to our rules, all we're using is the power rule, the sum and difference rules. This is no good to us. In fact, because of this right here, that multiplication, it means we have a big problem, just like the division right here. We have to expand this function as much as we can, and then we'll differentiate it. So that was the weird thing about this one. In green, this is going to be the algebraic work on it. Let's call this new and better g of x. We'll go negative 5x. X plus 1 times x plus 1. So it's negative 5x. Boiling out x plus 1 squared will give us x squared plus 2x plus 1. Now we'll just distribute the negative 5x through that entire group, and we'll have exactly what we want, something that looks like this, where we can differentiate going term by term. This one is honestly the more annoying one because we had to divide again using exponent laws. Here, we're still using exponent laws, but it's just much, much more fast. Distributing negative 5x in gives us negative 5x cubed minus 10x squared minus 5x. So that's our function. Here, we can differentiate this in the normal way that we would like to. Other questions or comments so far, Bill? Okay, let's do the derivative in blue. And now we get to say the derivative. G prime at x is going to look like this. It would have the value for our first term. Awesome, thanks. That's exactly how that one will go. And same song and dance for the second term. Copy your negative 10. 2 comes down multiplying. New power on x is 1, so I'll just write it as x. Anyone have the last term, negative 5x? Good call, negative 5 immediately. And going with the same theme of, if you see something that's eliminated, just cross it off. You could do this on your paper, just as a reminder that that x is just gone upon differentiating. Much like with what we did here, if there's a constant just hanging out, gone. If this helps you to notate it, that's probably a good strategy. So it looks like we're just about there, folks. All we need to do is write this as negative 15x squared minus 20x minus 5. And that's finally our derivative on this one. Much nicer than the division here, but division has its own issues, so we just work with it and survive. Any last questions on getting through these so far, folks? Okay, well, I think we got through the main kinds of issues that I want to talk about today, but how about just one extra one, just for a bonus? Does that sound all right to folks? Okay, this one will be part D. And the function goes y equals 2x minus 5x fifth root x squared plus 9 to the x. So Really bizarre function for sure. I think the hardest thing about this function would be coming up with the word problem that goes along with it. I just think of it as random math at this point. But if we're going to differentiate it, I like the 2x. That's just going to turn it into a 2, so no problem there. I hate this. That has to be corrected in a big way. And that was not so bad. We have a formula specifically for that exponential function. But first, let me write down an exponent law. If you have the nth root of x to a power m, it comes in this way. X to the power of m divided by n. Essentially, the root is telling you the denominator when you go to write out the fractional exponent. So when we go to fix this, here's what we can do. Let's call it y equals 2x minus 5x times. Now here, this was x power 2. But because we're also taking the fifth root, we divide by 5. Now let's go back to this x right over here. X is to the power 1, but we have to combine these two bases to get x in one position. So let's say that power 1 is 5 over 5, just so that we have the compatible denominators. Then plus 9x, that one was always good to go, so we'll just copy it in again. Last thing to do is, let's just simplify on the last bit. We have 2x minus 5x to the power. We're taking 5/5 plus 2/5 to get 7/5 plus 9 to the power x. Now, this function was not so bad. The problem was really right here. But it corrected to this stage, and in that form, we're ready to differentiate. The variable of x is in one position, and so the power rule just is going to make short work of these first two terms. Well, let's see what happens. Let me get some extra space here. Oh, geez, there we go. It's going to be either y prime or dy dx is completely interchangeable. Let's go down the line. Derivative of 2x will just come out as a 2. Then minus, here's where it gets a little bit more interesting, but not too bad. It'll be the constant 5 times the exponent of 7/5. And now we have to write x to a brand new power. Always, no matter what, we're subtracting 1. But if it's 7/5, we're taking 7/5 minus 5/5 to get 2/5. Then last, we need the derivative of that thing. That one completely breaks the pattern we've been seeing of differentiating all these power functions, like say the x cubed where the 2 came down. Watch out for these because sometimes it just kind of, we don't expect it and we can use the wrong rule. Anyone recall how this one is going to come out? Exactly. Good call, folks. It's going to be itself, and then you put a corrected term here. Because it wasn't e to the x, we multiply by natural log 9. Finally, that is the full derivative of this one here. We'll just simplify and say y prime equals 2 minus 7x to the power of 2/5 plus 9x times the natural logarithm of 9. We've got it, folks. That's our pretty nasty derivative this time, really because of the 9x and the odd exponent work we had to do right here. Any questions at all, folks, on getting through these? Okay, well, I want to switch gears, talk about a couple additional topics, and then we'll call it a night. The next thing we want to take a look at is we always need to remember, we haven't been talking about it much today, but I hope you've been thinking about it. Every time you calculate the derivative, this new function will give us the slope, the tangent line of the original function in black at any value of x. So if you graph this thing, and maybe you're wondering what happens when x is 5, plug 5 down in here, and there you have it. That will be the slope of the tangent line immediately. Kind of a nice little process. With that in mind, let's do that again. Example 2, we want to find the equation of the tangent line to that specific curve. Let's take a reminder though, because we have done these kinds of problems recently. It's on the homework that's due today. When we were in section 2.7, that's the first problem we did. We took a function, y equals x minus 5 divided by x plus 3. We wanted the equation of the tangent line. And to do that, we had to crank out all of this stuff right here, only to get a slope of 1/2. The good news for us is this becomes very, very short work. You don't ever have to do this again, even if the instructions say this. The only way I would force you to go through these processes is if it said by using the definition of the derivative. So that's only going to happen once on exam 1, essentially. And all you're doing is differentiating, not finding the tangent line. So back to this one, here's what the process is going to look like. As a step 1, we start off by just differentiating the given function here. So let's call that dy dx. First thing that happens is we have a power function, x power 4. So this becomes a 4x cubed. Now we are using the sum rule. We're going to put down a plus. Here it's a constant multiple rule since 2 is multiplying. And next, derivative of e to the x. Good call, e to the x. It's our world's best derivative, essentially. And we're done with step 1. We've calculated the derivative. On to step 2. Here's a notational reminder for stuff we'll see here and there. We want to calculate a slope. It's going to be the derivative of y with respect to x. And this is the evaluation bar we mentioned last class. It means I'm taking this stuff, I'm going to evaluate when x equals a particular number. We go up here and only just grab the first coordinate, 0. The second coordinate is just the full point that that curve is going to go through. So we'll say when x is 0, go back over here and plug 0 inside that first derivative. It'll be 4, 0 to the power of 3, so that term's gone, plus 2, e to the power of 0. So this whole thing turns into 0 plus 2 times 1. We get a value of 2 exactly. The 1 right here is from e to the power 0, turns into a 1 altogether. And so now we have a slope m, and we're off to step 3. So in step 3, I'll just use my favorite way to build a line. I usually go y minus y1 equals the slope m times x minus x1. I mentioned last time we did this, if you build your lines in a different way, don't change. If that's the way you like to do it, then that'll be terrific. So our x1 is this 0 here. Y1 is the 2. And the major thing that we had to calculate was the slope m. That's really the whole question in a certain sense. So it will go y minus the 2 for the y1 equals a slope m of 2 multiplying x minus 0, which is our x1. So the right-hand side is just a 2x, add 2 to both sides. Our tangent line equation is y equals 2x plus 2. And so let me fix this one bit right here. It's always good to emphasize the slope because that's what the derivative in step 2 always gives. It's a brand new function returning a slope of 2 at any point you specify using that first coordinate. Now, whenever you do this problem, say as a homework problem, less so as an exam problem maybe, what you would want to definitely do is check it out. Let's see how likely that is to be the right value. Should probably zoom in, out. So this can be really fast. Just type it in directly into your favorite graphing calculator. It doesn't have to be Desmos. Y equals x power 4 plus 2 e to the x. So that's our strange looking curve right there. We're interested at 0, 2. Let's double check. That's the coordinate 0, 2 that they gave us. Now, next thing we put in is our tangent line equation. Y equals 2x plus 2. And to me, visually, yeah, that looks like a bona fide tangent line equation. You don't have to produce a graph. You don't have to draw it on your paper. But this is more of a check. Because if anything here is even just a little off, say our slope is 2.1 for some weird reason, we don't have the right line. You might have saw it move, But if you zoom in enough at 0.2, you'll notice it's just not quite right. The more you zoom, these lines are supposed to become more similar. And they're not, they're staying different. Correct it to 2, suddenly it's the one line we're expecting. That's what the derivative will give us. The tangent line will be the best local linear approximation to that original curve, in the sense that, well, zoom in enough and there is very, very tiny separation between that original curve here, y equals x4 plus 2e to the x, and the simple tangent line. So that's our redo of the tangent line equation. Any questions at all, folks, before we return to our last question? Yeah, go ahead.
So does it technically give the exact line that's into the curve, or is it technically so close that not important?
It will give the exact line, exactly. The tangent line equation is always a unique equation if your function is differentiable. So there's only one way to get that to come out just right. It's got to be that line there. Other questions at the moment? Okay, well, let's go to our application for the day. This one I stole right out of our book. I think it might be in chapter 3 somewhere. I might come back in chapter 4. But here's what the context is telling us. They say biologists have proposed a cubic polynomial, cubic because the power there is 3, to model the length L of an Alaskan rockfish at AJ. So some Alaskan fish, the rockfish, you can use this as a model for how long it's going to be, its length, and I believe they said inches, based on how old it is. A might be 10, 12, something like that. So let's take a look. L is measured in inches, A is in years. We should return to that. I'll highlight it. First thing we want to do is calculate that quantity right there. Then we'll give a practical interpretation using the context, which think of this one as kind of a preview or warm-up problem. First thing we do is exactly what we would expect to do in this section. We're going to differentiate a rather large-looking polynomial. But if it says to calculate dLdA, evaluated at A is 12, really you're just doing this, L prime. So that's a reminder, it's just Leibniz notation indicating it that way. It's the same as dLdA. But it turns out in these kinds of situations where your independent variable is A and your dependent variable is L, Leibniz becomes a really, really good idea. This is where Leibniz notation starts to shine quite a lot. So if you call it L prime, you're considering A to be the independent variable. If you call it this way, there's no question. The independent variable is always in the denominator in Leibniz notation. So either way we call it, we go up here and this is what we do. That's a power function. So 3 will come down and multiply 0.0155. And the new power of A is power 2. Then same exact strategy. Copy the constant, which is negative 0.372. Will be multiplied by 2. I'll use parentheses to indicate multiplication. And the power of A is now 1. On this one, this is where it gets fast. That's just a 3.95 because the power of A is 1 right there. A cancels off essentially. And this is a constant. The derivative of constant is always 0, so we just ignore it at this stage. So here's our values. And I did put these in a calculator before I came today. I decided you probably wouldn't find it interesting to watch me calculate these values. So I got dL, dA came out as 0.04. Oh, geez, let me take a look. 0.0465 A squared minus 0.744 A plus 3.95. So that's our derivative. Next thing we need to do is the evaluation. That vertical bar says, take this and plug 12 in wherever A occurs. Any questions first about the derivative though? Okay, so now next we're going to evaluate right at this value. A is 12. So the derivative of the length of the rockfish with respect to the age of that rockfish, evaluated at 12 years old, comes out in this way. Again, this is just a fancy way to indicate a function evaluation. Go to where A is and plug in 12. 0.0465 multiplying 12 to the power 2 minus 0.744 times 12 plus 3.95. Then this all together, when you jam into the calculator, I got 1.718. Well, we've got it, folks. One thing I didn't put in here, though, is now that I have this, the next thing we need to do is interpret our answer. And interpretations are always easier if we throw in the units. Anyone see what the units might be for 1.718? It'd be inches per year. Good call. The inches come from the numerator and the year comes from the denominator. That's the second way Leibniz notation is really helpful. It tells you the units immediately. So from here, we had L in inches. From here, we had A in years, and that's why we get inches per year. So that kind of setup will work each and every time we do this kind of process in Leibniz. We just wrote L prime, no harm done either, but we have to think in these terms to get the right value out. Slightly trickier in my opinion. Now we're ready for the last part, putting down an interpretation to this thing. First, any questions at the moment? Okay. First, I'm going to say out loud a wrong answer. Please don't write it out. But this is the easy mistake to make on this problem. That's because we're just not used to derivatives. We're used to functions where you just evaluate with function notation. So the wrong interpretation is a 12-year-old Alaskan rockfish is 1.718 inches. Doesn't even sound right. I didn't even use the right units, right? Inches per year. The correct interpretation would go a little bit more like this. When the rockfish is 12 years old, next thing I want to throw in is a sign on my number. That's a little bit weird, right? I mean, it's positive. You don't need a sign to dictate it. But I'm only doing it right here just to help out in case it was negative. We would have had to say something else on my next line. So when the rockfish is 12 years old, I'll say it's growing only because it's positive there. If that was a negative, I would have said it's shrinking. So let's say it is growing. Let me highlight in yellow to tie together why we said growing, because of that positive sign, at a rate of, now we just go back to this quantity and just state 1.718 inches per year. So that's our interpretation of that quantity. And we expect if you put in something other than 12, you're going to get a different derivative right here and a different interpretation as well. If we said 5, I'll have a different number here, and I would say when the rockfish is 5 years old, it's growing at this new rate down below. So the rate of growth of the fish will depend on the age in this particular way right here. So this problem was kind of twofold. Our major thing was really just calculate a derivative when it's not x's and y's. But this is the hard stuff right here, in my opinion, getting used to interpreting the derivative. Think of this as a first practice, and we'll return to it a lot in chapter 3, and particularly in chapter 4. Well, any last questions, folks, on getting through this application problem here? Okay, well, looks like we've done it for the night. This is the end of the notes. And just as a reminder, back on the Moodle website, our next exam will be on Monday. It is an open calculator exam. These are the calculators that are allowed, but if you have a scientific calculator that's similar to one of those, just send me an email. I'll take a look at it, send me like a screenshot, and if it's a non-graphing calculator, non-cell phone, then it's probably just fine. So if you have a calculator you really like, you're welcome to bring it to class. And your calculator has to be one of these two kinds. Also, you're allowed to have an entire page of notes, size 8.5 by 11 inches. So this size. Front and back, you can put anything you like on it. Formulas would be a good idea. Other kinds of things, maybe motivational poems and stuff could be helpful. I won't be collecting your notes, so it's going to be all up to you. And after you do this page of notes, it'll be the same thing on exam 2, exam 3. I suggest you keep all those notes together. And when you go to do the final exam, you can consolidate and have one master page of notes for the overall cumulative exam. So just a couple more reminders about the exam. These are the sample problems on this file right here, but that is a long set of problems. The real exam is going to be short. It's only 60 minutes. The extra 7 minutes of the class is just for checking your answers. And no one problem can get really nasty because I realize we have to move through it to get on to the next. So some of these problems are a little bit harder than what I would really ask on the real exam. So if you see a nasty one, think of that as that one's just for practice. Well, any last questions at all, folks, about exam or otherwise? Okay, well, have a great night, everyone. If you're working over the weekend, don't hesitate to email me. I'll be happy to help out, especially since it's an exam week, I'll be available. And if you want to get together on Monday for any extra practice, my office hours are here, and you can email me if these times don't work.
I was doing almost, and I cannot figure like any of the problems in 2.7.
Yeah, 2.7 is nasty for sure. So on, say, this one right here,
No,
it looks more like this one,
Yeah.
actually.
these, I got 23 just fine, but 5, 7, and 13.
Okay, let's take a look. Starting at 5, you have an equation, that point. This looks like a great setup. And f of 3, as a trick, it's got to be 4 because of that provided point.
Oh,
So good call in there. 3 plus h would go in that location squared, and that location minus 5. So your setup looks great on this one. Then let's see, 9. So by 2, you should get 18. 6x by 2, 12. Then h squared, 2h squared looks good. Negative 15. And then, let's see, I think there might be a mistake from right here. When you go to the next line on this, all this looks good, except for right here. We should go just a minus 5h on that, and then a minus 4. So right here, there should be a minus 5h.
where did the -5? Oh, wait, okay, yeah.
That makes sense so far?
Yeah.
Awesome. Then with what you have here, let me take a look. So there's 4. Yeah, I see what you mean. This seems kind of odd for some reason. X plus 1, h is going to 0. Now I'm going to check my work on that one. This was section 2.7. This is problem number 5. And I got 18, 12h, 2h squared minus 15h minus 5h minus 3. How did I get a minus 3? Let me check out one extra thing. Yeah.
I didn't staple this, but I'm kind of in. Maybe okay.
Yeah. If you like, you can just put like, say, your initial on all the pages and you'd be okay. But I usually don't separate the pages, so it's not a huge worry.
And then where should I go first?
I would say that's a good question. You can leave it like the
Thank
stack
you.
right there. Thank you.
I might just stick with turning mine in digital because that way I can keep the notes on my phone.
That's very helpful. Yeah. Okay, so 3, 4. I've got 3, 4, 3, 2x squared minus 5x plus 1. Man, I am not seeing it on this one. Let me just go through it with you if you don't mind, if you got the time. So if it's y equals. It's making a mess of our stuff here. So we've got 2x squared minus 5x plus 1 at the point 3, 4. So we take the limit, h goes to 0, f of x plus h minus f of, oh, I said x plus h, but it should really be at 3, minus f of 3 all over h. So we'll have lim, h goes to 0. 3 plus h going inside here would be 2. 3 plus h squared minus 5, 3 plus h plus 1. Let me take a look so far. Oh, you did have a plus 1 right here. Gotcha. Oh, I think that is what I was missing when I was taking a look at my work. Sorry, I couldn't find it at first, but I think I
Oh,
see
the
it.
plus one make it a -3.
Yeah, it should have been a -3 right there.
Okay.
So it should look like this. Let me keep on going through it. Let's see what this turns into. Then h goes to 0. Then 3 plus h squared. It's going to come in as a 9 plus 6h plus h squared. Then we distribute 2 through like you did. We should be getting 18 plus 12h plus 2h squared. Through here is going to be minus 15. And, oh, I think that was the next thing. This should have just been a minus 15, not a 15h.
Oh,
And then minus 5h plus 1 minus 4 all over h. Sorry, I must be getting tired. I couldn't quite see that the h there was the issue. But now 18 minus 15 takes us to 3. And that's our -3. So all of these would actually cancel out. Then these just have h's. Now you can cancel your h's and take the limit at that stage.
go. What's going on?
Question over here?
Well, I was just gonna, this is the personal calculator. This is my favorite calculator. I had it since like high school. And I was like.
I think I'm familiar with this one. I'm not good at picking up
It's
the
a
dust
TI
cover.
30.
Yeah, this would be a great one. Yeah.
It's my favorite. This is the one I like specifically, the TI 36 Pro.
Yeah, that'd be just fine.
I love this one specifically because it's so good at holding numbers.
Oh, storing it and stuff.
Oh, yeah, especially when, because I have the version that you, that's on there, but this one I like more because of say, like, there's a fraction on this one, which helped me calculate, which was on all one, which is the 4, like was 7/4. And if I was gonna have times it by 2, 10 to 2, and then it would bring it to an instinct, which was 7/2. And this is why I like it. It's so good at holding numbers.
Yeah, I like that too.
I just like it because it's just so familiar with it. I had it for like 4 years now.
I get the same with my calculator. I have a TI-84 that I've been using for about, I don't even know anymore.
My
Yeah.
mom found like the super calculator for like $12.
Mhm.
Cause I got a margin, it's like, I get it, but I can't use it for any test period.
Yeah,
It's a super calculator, you know?
gotcha.
And all I'm here is just to see if I got any of this stuff right and still on.
Gotcha. Anyone in particular?
Yeah, just all the ones that are squared and they're squared.
So is this the original function and that's the derivative?
This is the original function, this is the answer.
Gotcha. That looks great. That looks great. On this one, I'm not sure what the original one was. You've indicated the derivative.
Well, this one is, it's the same answer, so I was like.
Oh,
yeah.
gotcha.
And these ones I'm not sure because it's the same answer or not.
I would say this one is a tricky one. Before you can differentiate this, you have to write 1/t as t power -1.
Yeah, I didn't fully understand this one. I just wondering if that's even correct.
It has to be written as this way. So 1/t is t power -1. And so now if you differentiate with respect to t power -1, you'll get negative t power -2. So this should
So
be,
that should be 2 instead.
this one right here. I think this one should be, that one there came from 1/t squared, which is t power -2. You differentiate that one with respect to t, you get -2 t⁻³ on that one there.
And so that would basically change that from one to two then.
Exactly, yeah,
Okay, that makes sense now.
cool. You would also have a negative in front of that.
Also, this one, it looks funny because the W isn't included in this, so I'm like wondering if it's this minus this, which would then be basically cancel each other out.
So it only cancel, this also had a W.
Yeah, but that one has a W on the homework. It looks like the W is outside of the square root. So I'm like wondering if W is separate.
It would be considered separate, but still multiplying, yeah.
So basically, in order to get rid of this, I would just have to divide it by -2 squared.
Divide which part?
This, I would have to get rid of this.
But why would you have to? Was this the original question?
Yeah, this is the original question.
I would just leave it as is. It's just a constant.
Oh, so that's just fine then.
Yeah, when you go to differentiate this, that constant just stays right where it is.
So it has no harm. So
Yeah.
even if it's a square root.
It could be a crazy looking constant, absolutely.
So it could have even looked like square root, like 400 to W, and it would
Yeah.
be just fine.
Or natural log 12, something bizarre, yeah.
So as long as it just looked just fine, it's still connected to it.
Exactly.
Then I'm just gonna square that, that's the answer.
I'm gonna take your question over here, then I'll return to you. Sound good? Okay, question over here?
Um. Here is. Well, so it's 2B, supposed to be, I got the question.
Mm,
So the limit as x approaches 0, q of x here doesn't exist.
Yeah,
And so, yeah, I've got that, and I just want to make sure, you've circled it, and I want to make sure that I've not missing a big concept here. Do I say the whole thing that doesn't exist? Am I subtracting?
yes, exactly. So that one piece doesn't exist, and that means the whole answer is it does not exist.
Full answer is it doesn't exist. Huh?
Yeah.
Okay, cool.
Essentially, if one part's undefined or does not exist, all of the math around it is meaningless,
Okay, cool.
sadly.
Thanks, yeah, I want to make sure.
So how are they coming over here? Did that one work out?
Yeah, I got 7x minus 17.
Awesome, cool.
And then with 7, I also didn't understand it.
So this one right here, same kind of idea, 2 plus h minus f of 2. And yeah, that's a little trick right here. F of 2 is just got to be that -4. So that looks good. And now if you put 2 plus h here, 2 plus h plus 2, 2 plus h minus 3, that looks great. Got the 1 over h in front. So h plus 4, then it's going to be, let's see. On this, there's just a tiny mistake on the h minus 2. It should really be a h minus 1 coming from here.
Oh, is it? Oh, okay. Oh. I get it.
Cool. That's probably the only thing that was throwing the numbers off. So that means this has to be h minus 1 above and below.
Is it 2 right though?
The 2 right here.
Mhm.
Let me take a look. It started as a -4. I believe it should still be a -4 right there. Just above, but not below.
And then would I put the 4 down here or no?
It would just be the no 4 down there, just the h minus 1.
Yeah, I just didn't get any of it. I was looking at.
I'm looking at your work and you understand the concept. It's just tiny little things that are preventing you from getting the next step.
So then I'd multiply this, and then would it be h plus 4 plus 4h minus 4?
Yes, exactly.
Or this will just be h minus 1?
It'll be the h times h minus 1 in parentheses in the denominator. So you're pretty much just copying that once and then multiplying that right in there.
Right. So then this turn into 5h over h minus 1.
Yeah, it's looking good. So you have h or h, so 5h then you have a cancellation here to here. You still have the limit as h goes to 0 right in front.
So then would this turn into, -5?
Exactly, yeah.
And